Now, let us solve some questions on hydrogen spectrum. Okay. So let us go for this question. The difference between the wave number of first line in Balmer series and last line of Paschen series for Li+2 ion is. Okay. Now look at this. See, they are asking you the difference between wave numbers of the first line in Balmer series and the last line in Paschen series for lithium plus. Let us write them one by one. Coming to the first line in Balmer series. See, I told you very clearly that for Balmer N1 is a 2. And see, when they are asking for first line, nothing but H alpha line, add 1 to your N1, then N2 will be 3. Okay. So N1 is 2 and N2 is 3. Of course, for Li+2 anyway, that is equal to 3. Right. Coming to the last line in Paschen series. I told you that last line in any series is called a series limit. Okay. Now coming to Paschen series. For Paschen N1 is 3. And because this is series limit, N2 is infinite. Of course, even this also is for lithium+2 only. So let us consider these values and calculate the wave number. I hope you know that the expression for wave number is RH into Z square into 1 by N1 square minus 1 by N2 square. Let this be case 1 and this be case 2. Say for first case, nu bar can be written as, keep RH as it is, Z square is 3 square, 1 by N1 square is 1 by 2 square by 1 by N2 square is 3. Right. So this can be written as RH into 9. And how about this? Take LCM, 4 into 9. Now, this will be 9 minus 4, right? Then simplify this. This 9 and 9 get cancelled. So we will get 5 RH by 4. Is that right? Now this is case 1. Come on, go for case 2. Nu bar is equal to, now using these values, nu bar is equal to RH into, again Z square is 3 square. Now 1 by N1 square minus 1 by N2 square. You know, 1 by infinity is a 0. So this is 0. Come on. So this will be RH into 9 into 1 by 9. 9 and 9 get cancelled. So this comes out to be RH. Now they are asking the difference, right? So difference can be given as 5 by 4 RH minus RH. Yes, it will be 5 RH minus 4 RH by 4. So that comes out to be RH by 4. Okay. So this is what. You should know the values of N1 and N2. Of course, the value of Z. You all know what the N1 and N2 values are. I've given examples yesterday. Now the expression. That's it. If you know these things, you can solve any type of problem. Okay. Now, let me go for one more. This is interesting. If the shortest wavelength of Lyman series of a hydrogen atom is X, then the wavelength of the first line of Balmer series of hydrogen atom will be how much? So here there is an interesting point. Of course, the series are known ones. In both the cases, it is hydrogen atom. Now, in the first case, they are asking you the shortest wavelength. But in the second case, they are asking you the wavelength of the first line. Now, let us see the N1 and N2 values for both the cases. Come on, let me say what shortest wavelength is. You know, when we go for shortest wavelength, of course, this is in Lyman series, right? When I say shortest wavelength, remember energy difference is maximum because energy and wavelength are inversely proportional. They want the wavelength to be shortest, then energy difference must be maximum. So when you want a maximum difference in energy, come on, look at this. You know, for Lyman series, anyway, it is 1. N1 is 1, we know that. But you want the difference in energy to be maximum, then take the last one. Because you want the difference to be maximum. Got it? So this is very important. Let me put a star mark. If suppose they ask for longest wavelength, remember energy difference has to be minimum. Then in that case, N2 will be the next immediate. Ante, I mean, it will be 2. So if you want the maximum difference, you take first and last. If you want the minimum difference in energy, take first and immediate next. Hope you got my point. Because this is Lyman series, N1 is equal to 1. Now coming to the first line of Balmer series. This is the basic one, a regular one. First line of Balmer series. You know N1 is equal to 2. N2, because it is Balmer series, I have written N1 as equal to 2. Okay. Now they are asking you for the first line, nothing but H alpha line. So just add 1. See, they ask for first line, add 1 to your N1. Then that will become 3, right? Now we can straight away go for wavelength expression, or else if you are okay with your nu bar expression, go with that. Then finally we will convert that into wavelength. Now we know that the expression for nu bar is equal to RH into Z square. Here in this case it is 1 square into 1 by N1 square minus 1 by N2 square. I am taking the first case into consideration. Okay, now this of course is given as X. Check out the question. Now, what is this? You know this 1 by infinite square, of course it is 0. Now what do you get? This is nothing but RH, and it is given as X in the problem. Now taking this RH value, nothing but X, we will calculate. No, just a second. This is not X. We got RH, but see, they have given that the wavelength is X. Nu bar is RH. Then we know that lambda is equal to 1 by nu bar, nothing but 1 by RH. Now, yes, this is given as X. Because it's not the wave number that is given as X, it is the wavelength which is given as X. Got it? Now, anyway, we have finally given the value of lambda. Now let us go for the second case and find the wavelength of the first line of Balmer series of hydrogen atom. Even here also let me take nu bar again, because nu bar is little bit convenient. RH into Z square into 1 by 2 square minus 1 by 3 square. RH into, now this can be written as 1 by 4 minus 1 by 9. Taking the LCM and all, we get 9 minus a 4 by 4 into 9. Nothing but 5 by 36. Right? So from this, lambda can be written as 1 by RH into 5 and by 36, and that 36 of course goes into numerator. Is that clear? Look at this. Nu bar is equal to 1 by lambda. So lambda is equal to 1 by nu bar, and this is your nu bar. 1 by RH into 5 by 36. So 36 has come into numerator. Now, anyway, we got the value of 1 by RH as X. Substitute that here. Right? So 1 by RH is substituted as X. So your answer will be 36 by 5 into X. This is very interesting. Check out the problem. Only thing is, you should know the N1 and N2 value. Just with the value of, with the expression of nu bar, you can calculate all the variety. See, we have not gone for the value of lambda, the expression for lambda, but still we could solve the problem because nu bar and wavelength are related. as mu bar is equal to 1 by lambda, right? Next. Okay, we'll go for one more problem. Which is again very interesting. Come on. The wave number of first line in a Balmer series of hydrogen atoms is 15,200 per centimeter. The wave number of first line in a Balmer series are lithium +2 ion is. This is interesting. This is where you have to be very logical. See, in both the cases, it is the first line in Balmer series. But in the first case, the atom or the species is hydrogen. In the second case, it is Li+. Let me tell you how to solve this. Again, going for the wave number. So nu bar is equal to RH into Z square into 1 by, of course, N1 square minus 1 by N2 square. Now, let me tell you that RH is a constant. Even if you consider they just get cancelled, RH is a constant. You know, because line and the series are same. Even N1 and N2 are same. Okay. When N1 and N2 are same, you know, we have only one thing left. See, you can cancel out this. You can cancel out this, right? Because RH is anyway a constant. N1 and N2 are same. So what is the thing left out? Removing the constant, you know, this can simply be written as nu bar is proportional to Z square. Check out the thing. Removing the constant. You can simply write the proportionality. I told you this earlier also. If you want to remove the proportionality, use a constant. If you are removing constants, use a proportionality, right? So from this, we can simply write it this way. Nu bar 1 by nu bar 2 is equal to Z1 square by Z2 square. Nu bar 1 in the first case. Nu bar 1 in the first case. Look at this. 15,200. Nu bar 2 is what we have to calculate. Then Z1 square. In case of the first one, Z is the 1 because it is hydrogen atom. Z2 square. In case of lithium plus 2, it is a 3 square. Is that okay? Now nu bar 2 is equal to 15,200 into 9. So this comes out to be 136,800 per centimeter. Okay. So this is how you have to actually solve this applying the logic. Because no, every time you cannot substitute all the values. Even without writing the RH, N1 and N2, you can solve problem this way. Remove the common things. Common things in both the cases. You got two cases. But in both the cases, it is the first line in Balmer series. Even if you write, they get cancelled, right? So no use of writing that. So therefore, you can just remove that and you can simply solve it. Okay. Now, let us go for the next one. Now let us solve a problem on number of spectral lines. Of course, I gave you this when we discuss the theory part, but still we will solve a question on that. Right. Look at this question. The electron present in fifth orbit in excited hydrogen atom returned back to ground state the number of lines which appear in Lyman series of hydrogen spectrum is okay. Electrons are present in fifth orbit. Now they return to ground state. So you can calculate the total number of lines, total number of spectral lines, but they're not asking the total number of spectral lines. They are asking only the spectral lines formed in Lyman series. Let's see. Yes, that's it. This is the first orbit, this is second, this is third, this is fourth, and this is fifth. Now, simple thing. You got your answer. Only the number of lines formed in Lyman is what they are asking. So, number of spectral lines formed in Lyman series is 4. Isn't it simple? Come on, let us give some extra information. You know, here you get 3 lines in Balmer series. Lyman in UV, Balmer in visible, then of course go for Paschen. You get just 2 lines in Paschen series, R near IR. And then this is bracket series. Only 1 line in brackets. This, of course, in middle IR. Okay. This is all about Lyman, Balmer, Paschen bracket. You get 4 lines in Lyman. So this is your answer. Okay. Answer is just 4. Okay. Next. Look at this question. What the transition in the hydrogen spectrum would have the same wavelength as the Balmer transition n is equal to 4 to n is equal to 2 of helium plus a spectrum. Interesting. See, they are asking the transition, nothing but the N1 and N2 values. In case of hydrogen, that will have the same wavelength. For though they have asked the same wavelength, we will be calculating again in terms of wave number, which is more convenient. Okay, as the transition in helium plus a spectrum, that is Balmer transition from 4th to 2nd. See, because the difference is 2 here, let me call this a second line in a Balmer series. Or I can also say that it is a H beta line. Okay. Now let's see. See, when wavelengths are same, obviously, even wave numbers will also be same. So therefore, we consider wave numbers in both the cases. Coming to the hydrogen case, RH into Z square into 1 by N1 square minus 1 by N2 square. Because we don't know what N1 and N2 are. That is what they are asking. The transition is what they are asking in case of hydrogen. This is equal. Of course, I am taking nu bar in case of hydrogen. The second is nu bar in case of helium. Obviously, when nu bar is same, lambda will also be same, isn't it? Now, in case of helium plus RH into Z square, helium plus, so Z is 2, then 1 by N1 square, the lower energy level, minus N2 square, the higher energy level. Hope this is clear. So RH get cancelled. Now this can be written as 1 by N1 square minus 1 by n2 square is equal to, say this is 4, this is 1 by 4, and this is 1 by 60. Okay, so now let us, of course, simplify this further. We can straight away write, we will just multiply this. Check the way I'm writing. This can be written as 4 by 4 minus 4 by 16, right? Now this will be 1 and this will be 4. Now compare these two. See, when you compare these two, n1 square is equal to 1 and n2 square is equal to 4. Correct? Because 1 by n1 square is 1 by 1. 1 by n2 square is 1 by 4. So n1 square is 1 and n2 square is 2. Therefore, n1 can be given as 1. N2 can be given as 2 because n2 square is 4. So n2 will be only 2. Now looking at these two, we can clearly say that the line is first line in Lyman series. Isn't it? Because n1 is 1, therefore Lyman. Difference is only 1, therefore first line. Right? So first line in Lyman series of hydrogen spectrum will have the same wavelength as the Balmer transition 4 to 2 in case of helium. Got it? Next. This is again very interesting. Okay. Coming to the next one. Yes. Come on, we'll go for this question. One second. Calculate the energy emitted. Solving a problem on energy. When electrons of one gram atom of hydrogen undergo transition. Giving the spectral line of lowest wave energy in the visible region of its atomic spectrum. This is interesting. We'll go for expression for energy now. But here there is one more interesting point. They have not just given one hydrogen atom, 1 gram atom of hydrogen, which will have Avogadro number of atoms, N0, or you can use N8 term. Okay. Okay. Now, giving the spectral lines of lowest energy in a visible region. So they have given something something indirectly. Visible region refers to Balmer series. Lowest energy spectral line. Come on, let us just go with this. Spectral line of lowest energy in the visible region. So when I say visible region, it is of course Balmer. From this, it can be written as N1 is equal to 2. I mean, the lower energy level in anyway is 2. Lowest energy, just now I took. If you want lowest energy difference, go for the next immediate. If you want the maximum energy difference, go for the last one. When you say lowest energy, you know, when energy is lowest, you can say that it is with the shortest, no, longest wavelength, right? Lowest energy is nothing but longest wavelength. So anyway, you got the N1 and N2 values. Yeah, this has to be N2. Correct. That's it for this. We have to calculate energy. We know that the expression for energy is N H C nu bar, where N is the number of photons. This we have considered as N0. Come on, write down 6.023 into 10 power 23 is N0, nothing but Avogadro number, into the value of H is 6.625 into 10 power minus 34 joule into second. Then velocity of light is 3 into 10 power 8 meter per second. Now the nu bar. Say you want the value, right? 109,677.8. But this is in per centimeter. Convert that into per meter by multiplying it with 100. So this will be in per meter. This is in meter per second. This, of course, is in joule into second. So you got all the things in SI system. Now this is anyway RH into what is the Z square? 1 square multiplied by 1 by N1 square minus 1 by N2 square. This is what you have to simplify. Okay. You know, finally your answer will be in joules. Let me straight away write the final answer. That will be 182.8 kilojoules. Yeah, simplification of course takes too much time, so I've just given you the final answer. Okay. Next. This is again on spectral lines, but there is some twist. In a collection of hydrogen atoms, all the electrons jump from, of course, n is equal to 5 to ground state finally. Of course, finally, but directly or indirectly. Now the interesting part, without emitting any line in Balmer series. Without emitting any line in a Balmer series. So nothing goes into second orbit. Nothing goes away from or out of the second orbit. So whatever comes to second orbit or whatever goes down from the second orbit are prohibited, are omitted. Let us see. The number of possible radiations is what they are asking. So this is interesting. The number of possible radiation. Come on. Let us take the question again. I mean the diagram again. Okay. Now let us first draw all possible transitions. Then we'll cancel out those, involving Balmer series. Come on. Okay. Lyman, then Balmer, then Paschen, and finally that is bracket. Correct. So considering this without emitting any line in a Balmer series. So when I say this, remember the electron cannot go to second level and cannot come down. From the second level. So this is interesting. So cannot go to second level. So that means these three are gone. Because if something goes into second orbit, obviously it has to come down from the second orbit. Now when nothing is going into the second orbit, even this is also removed. Got it? Now nothing is related to Balmer. Neither going into Balmer nor going out of Balmer. Right? So the overall radiations possible, Number of possible radiations can be given as what? The remaining 3 plus 2 plus 1, only 6 are possible. Okay, so this is a special case. One more. Even this also is interesting. Find the value of wave number in terms of Rydberg's constant. When transition of electrons takes place between two levels of helium plus ion, whose sum is 4 and the difference is 2. So this is special. They have not given the N1 and N2 values straight away. Of course, helium plus, therefore Z is equal to 2. But what they say is the two levels have got a sum of 4 and a difference of 2. You can just imagine. Let us say this way. N1 plus N2 is 4. Okay. N2 minus N1 is 2. See, from this we can say that N1 must be 1, N2 must be 3, right? Now check out. See, the sum is 4. Difference is, of course, 2. It's a simple mathematical. Now this is nothing but the second line in a Lyman series, isn't it? Because N1 is equal to 1, it is Lyman. Because the difference is 2, therefore it is second line. You have added 2 to N1, therefore second line. Come on, they have asked you to calculate the wave number of this particular line in terms of Rydberg's constant for helium plus. Come on. Nu bar is equal to RH. Yes, this is what we have to do. Into Z square into 1 by N1 square minus 1 by N2 square. Right? So this can be written as RH into 4 into 1 by 1 minus 1 by 9. RH into 4 into LCM is 9. So 9 minus 1, nothing but 8 by 9. So this is 8. 8 into 4 is 32. 32 RH by 9 is your answer. Right. So this is how generally the questions are asked. If you are okay with the N1 and N2 values and the value of Z plus the expressions of